the problem that we're talking about is this question of finding a number which would appear in this equality between the derivative of the p-adic L function and the special value of the classical L function. I mean, one remark it's maybe worth making is that it's a theorem, maybe I think of David Rohrlich, that for the right choice of a character on the algebraic side, that number is non-zero, assuming that the so in other words, even if you happen to choose, you happen to be in a situation where the modular form that you've chosen, the classical value could be 0, for example. But there still is an L invariant because you can find some character twist to make that algebraic side non-zero, and then you have this supposed relation. Now, the question of whether or not, I mean, as Dinesh pointed out, I mean, all the L invariants could be 0, or some of them could be 0, but in fact, at least some of these definitions that I gave are not 0 for reasons having to do with the Galois representation associated to the modular form. So you don't expect the L invariants to be 0 in general. Also, this slide I noticed I skipped because I think the remote control took me 2 steps instead of 1, and it's a kind of an important slide. So let me just remind you that now the remote. This was the slide that I showed you. This is the idea is to construct this L invariant as the ratio of these 2 maps between one-dimensional vector spaces, one of which is non-zero. But I mean, and I mentioned that the way you define these 2 cocycles is to do this integral here. But and then this is the other one. So this is the one which is non-zero, and this is the one that sort of you take this guy over this guy, so log over ord, in order to get the L invariant. I skipped this one. This is another way of writing this thing, and I thought maybe since I skipped the Hecke operators earlier, I have a couple of spare minutes, and I thought I would just do a short, amusing calculation to show you how you kind of reduce these integrals to something. I'll show you what I mean here. Here's my calculation. Okay, so on the top, I'm in weight 2 just for simplicity, so I have no polynomial. It's just a constant coefficient thing. And you remember the h log thing was the integral from tau to gamma tau of this integral 1 over z minus x d lambda. That's the rigid analytic modular form recovered from its boundary distribution by this Poisson integral. So reverse the order of integration. And now you see this integral in here we can do, right? It's the log of z minus x. And we evaluate it from the z variable from tau to gamma tau, and we get this function here. So tau is now a constant in the p-adic upper half plane, picked at random, more or less. And we have this log of gamma t minus x over t minus x. Now, never mind whether this reversing the order of integration makes sense or not, although it actually does. But this function here, I mean, it involves the p-adic logarithm, but remember this tau is in the p-adic upper half plane, so an x is in p1 over k. So x is never equal to tau. Okay? And similarly, x is never equal to gamma tau, because these guys have to be rational, and this is irrational. So this function in here has no zeros or poles on the rational points of the boundary, and the logarithm is actually locally analytic. Okay? This version of the logarithm. So this integral makes sense. I mean, whether or not it's equal to that, I don't care. And formally speaking, if you work out what happens if you put in gamma 1, gamma 2, and you use the fact that these measures kill the constant functions, you find that this is actually a homomorphism in gamma in the weight 2 case. So it's a 1 cocycle into the trivial action. So this kind of formula is going to come up over and over again, the integral of log of gamma t minus x over t minus x. And this is somehow the reason why you should think of it as a period. You're computing a period of the modular form on the upper half plane by changing it into an integral on the boundary. Okay, that's maybe the way to think of it. And it's also maybe just worth remarking, you remember the other integral involved not the log, but the ord. So it's kind of a fun calculation to show this. That if instead of using the p-adic logarithm, you use just the valuation. Same function here. This turns out to be a locally constant function on P1. And you remember here that the values of this lambda f on an open set are basically given by looking at an edge in the tree. And so the value of lambda on the characteristic function of an open set in the boundary is the value of the corresponding harmonic cocycle on that edge. And it's more or less a computation. What happens when you try to write down this integral, using the fact that gamma tau and tau are not in the ends, but actually reduced to some specific vertices in the tree, you get a kind of a telescoping sum calculation here. And it turns out this integral is actually this sum, which was what I used to define. That should be a gamma, not an alpha. The sum that I used to define the other map. So in each case, we chose a kind of a logarithm, whether it was the p-adic logarithm or the valuation, and we integrated this rational function against the measure coming from a rigid analytic modular form, and we viewed that as a one cocycle, if you like, or in this case, just as a homomorphism. So I thought it's probably worth motivating these formulas by this. So if you look back here, when I wrote this originally, now I have the p of x in there. You see, this is another way of writing integral p of x log, and I've changed this. I mean, I haven't changed the sign, but I wrote it the other way. P of x log x minus gamma z over x minus z. And this is integral d lambda f. Okay. Whoops. And as I said, in the weight 2 case, you actually have a homomorphism of a character of gamma. And that's where you get this, this alpha. Okay. So I mean, this LT that I defined, I mean, it seems to fit formally into the kind of picture that you would want an L invariant to fit into. Namely, in weight 2, it computes log of Q over ord of Q, like it's supposed to. And it seems to somehow, I mean, it seems to somehow be defined in a way which relates log and ord. But if you think about it for a minute, it has basically nothing to do with the p-adic L functions. Because the p-adic L functions formulas that I put up earlier show you that the p-adic L function and the classical L function are computed as integrals in the classical upper half plane. And those, in fact, are integrals of the modular form that you might have been interested in SL2Z. And this connection that I used that says that if you start with a modular form on SL2Z of the right kind, then there's some kind of corresponding modular form on a Shimura curve which has the same Hecke eigenvalues. This is a very indirect relationship. These two functions are, I mean, one modular form is a modular form on a classical modular curve. The other modular form is a modular form on a Shimura curve, which is being p-adically uniformized. There's no way to connect them. So as a method of trying to prove anything, it's not a very helpful definition. And actually, if you look back at, I had that long list of L invariants that I gave earlier. I mean, for instance, the Fontaine-Mazer L invariant is built up out of arithmetic data. And you know, at first, I mean, if it were easy to relate arithmetic data to periods of Riemann surfaces, I mean, a lot of things would clear up. So that's sort of useless. And the Coleman's L invariant also is done by some kind of, that has the advantage it's on an actual modular curve. I mean, it seems to involve p-adic integration on an actual modular curve, but still p-adic integration. So again, not connected somehow to the modular symbols, which give you the honest complex numbers that you get as special values of L functions. And so the great idea, I guess, that Henri Darmon had, and which his student Louisa Orton used, I mean, Darmon first in weight 2 and then Orton in higher weight, to actually address this original conjecture, is to blend the modular symbols which live on the classical upper half plane with this whole circle of ideas from p-adic analysis. So let me talk a little bit about how that works. So here it is. blend modular symbols with p-adic periods. And I think actually this 1, 1 is supposed to be 2, 2 or something like that. I don't even understand this remark myself. But somehow we want to think about this thing as, we're somehow thinking about now, a two-dimensional thing. The classical upper half plane cross the p-adic upper half plane, and we have functions which are kind of complex analytic in one variable and p-adic analytic in the other, which maybe seems hopeless, but it kind of works out. So now we need some other machinery, and the groups which come up in this setting are these groups, SL2. You take matrices which have just denominator a power of p, determinant of power of p, or you invert p. Maybe you put a congruence condition on the lower left-hand entry, and maybe you take the gamma naught p twiddle means positive determinant matrices. Again, these have p integers which have denominators only involving p. And these are subgroups of GL2 of Q and therefore also of GL2 of QP. You can, in the whole quaternionic game, if you think back, the method for finding discrete groups was to take maximal orders and then take their units. And then you embedded that into the 2x2 matrices and you got a discrete group. Well, that's what's happening here too. These are kind of the units in certain orders in the split quaternion algebra, called Eichler orders. But, and they are discrete in SL2 of QP, but they have a bad, you see this? They are useless for uniformization. They have a bad property. And the bad property is that they contain matrices like 1, 1, 0, 1. That's a nice, that's a good thing if you're doing complex analysis. But in p-adic analysis, the map which sends x to x plus 1 has the property that if you iterate it, you get x to x plus p. And then if you iterate it some more, you get x to x plus p squared. And you iterate it some more, x to x plus p to the n. In other words, the orbit of a point under translation accumulates at the starting point. The action isn't discrete. So if you're hoping to take quotients, for example, there's no way you could use a group like this. And the groups that come from definite quaternion algebras, because they come from definite quaternion algebras, they don't have anything like this. That's why those groups work. But these work in the Darmon setting. These are much more closely related to the ones you use for the modular curves. Now, here's what we're going to do. We're going to make a new set of modular forms, which is hybrid in the following way. It's a function. This is the classical upper half plane here. We're going to make functions on the edges of the tree, taking values in functions on the classical upper half plane, which are kind of basically for every edge. If you evaluate your function on an edge, you get a cusp form of weight k, and you have imposed this equivariance property, basically. The gamma, which is that one of those groups I defined earlier, one of these, acts on both of these things. So we can ask that if you translate on the action on the edges of the tree, that pulls out to be the action of this thing as a modular form of weight k on the classical upper half plane. And we want, if you think of it as a function in the E variable, it's supposed to be a harmonic cocycle. And if you think of it as a function in the Z variable, it's supposed to be a cusp form of weight k on the classical upper half plane. And because of this gamma equivariance, you see if gamma fixes E, then you get the equation f of Ez is gamma f of Ez. Yeah. I was just going to say that, actually. The subgroup that fixes E is, at least if you pick the standard edge, the subgroup that fixes the standard edge is gamma naught of NP, the usual gamma naught of NP. That's actually easy to see because in the p-adic group, if you think way back to the first lecture, the stabilizer of an edge was an Iwahori group, which were the integral matrices, p-adic integral matrices, whose lower left-hand entry was divisible by p. And if you intersect that with gamma naught of Pn, the condition becomes, now these have to actually be honest integers, not anymore Z1 over P, because they have to be p-adic integers. And you've added a congruence condition to this lower left-hand entry. Not only do they have to be congruent to 0 mod n, but also now mod P. So in fact, this condition here, if you took the standard edge, you have a usual modular form for gamma naught of NP. The other edges are modular forms for conjugates of that subgroup inside SL2 Z. Okay? So, and you have this action where the group G, this is positive determinant matrices. It sort of acts on the edges the way the group acts on the tree, and it acts on the Z variable the way it acts on modular forms of weight K. And so we want invariant things like this. So these are here's a picture, right? We have these modular forms on every edge, and if you add up the modular forms leaving a vertex, you get 0, and if you reverse an edge, you get the negative of that modular form. Okay? So that's one of these two variable modular forms. Now, if this big group, SL2 Z1 over P, or the various modifications of it that I mentioned, they permute the edges of the tree transitively. That's not hard to see. So it seems like you have a lot of freedom to make these things, but in fact you really have very little freedom, because once you pick the modular form that goes on the standard edge, all the other ones are determined, because the group action now permutes everything transitively. So, but I mean, you can't do this at random, because if you, I mean, you define your modular form on the basic edge, you translate it around on the tree, and then you hope that the result is harmonic. Okay, the harmonicity is a condition. And if you try to figure out what it means to say that the thing that you get after you translate it around is harmonic, it's very nice, but it turns out that this is equivalent to saying that your modular form, which is on gamma naught of NP, remember, the thing for the standard edge has to be on gamma naught of NP, has to be what's called P nu. So P nu basically means didn't come from gamma naught of N. And the reason for that, I mean, here I mentioned a few of these things. This is just the fact that it acts transitively. It's determined by the value on the standard edge, and it has to be a cusp form of weight K for this group gamma naught of NP. But, so if you want to go backwards, you want to start with a modular form, you can translate it around to get something on the tree. Excuse me. And when I said this is the one in SL2Z, I said it doesn't permute, here I say it doesn't permute the edges transitively. A minute ago I said it did. The reason is that the edges, the SL2Z preserves the orientation of the edge. If I take the group which is in GL2, then you have something that reverses the edge. But still, the harmonicity condition forces a relationship between the value on an edge and on the opposite edge. So if you plug all this together, put all this together and sort through it, then you find out that your form that you started with on gamma naught of NP, if the resulting thing is going to be harmonic, you get a condition on the Atkin-Lehner operator at P, and also a condition sort of on, I mean, if you like, the UP operator, and also on a slight variant of the UP operator. And those two conditions that you translate from the harmonicity say, in the end, by Atkin-Lehner theory, that your form is nu at P. Didn't come from gamma naught of N. Okay? On the other hand, if it did come from gamma naught of NP and not from gamma naught of N, then there's no obstacle. This method works. Okay, so it seemed like we made a much bigger space, but in fact, this space of the harmonic functions with modular form values on the tree are just the P nu forms on gamma naught of NP in a fancy way. Now, what do? We take this thing and we get a really fancy modular symbol, which takes a whole bunch of variables. Now, I'm drawing it here in the higher weight case. So the variables that it takes are, well, first of all, the R minus S is the modular symbol itself, and the E is an edge of the tree, and the P is a polynomial. And so what do you do with all this stuff? You take, so the E is going to give you, you take the modular form on that edge E, you multiply it by the polynomial P, and you integrate it from R to S, and you get a complex number. Okay? So this thing, for every path in the upper half plane, edge in the tree, and if you want, you can, if it's K is 2, you can forget this part. Just leave out the polynomial. Then you would just get numbers. And because of the fact that the modular form was harmonic, actually, for fixed R minus S, if you fix the modular symbol, and let's say you're at weight 2 maybe, so there's no P, and you just think of this as a function of E, you get a harmonic function for sort of trivial reasons. I mean, think back to my picture. You have the modular forms leaving a given vertex. They add to 0. So certainly their integrals from r to infinity in the upper half plane add to 0. Okay? So this converts that space of p new forms, given a path in the upper half plane, into a harmonic function on the tree. So you have a choice. You can think of it as a harmonic function with values in modular symbols, or you can think of it as a function from modular symbols into harmonic functions on the tree. Both points of view sometimes are worth keeping in mind. So here's a restatement of that, and this is just your E tells you to transform your modular form to figure out what goes on that edge. The R and S are the limits of integration in the upper half plane, and the integrand is the F that you're supposed to integrate times P of Z. And if you divide out by these periods of the space of modular forms, then this is actually a number. Okay? And the really amazing thing, although if you go back through the proof, it's true for kind of trivial reasons, is that this is a bounded harmonic function on the tree. So take k equals 2, right? Then you have a bunch of numbers. Why is it bounded? Well, it's bounded because, well, you remember that the modular symbols themselves were bounded. And you have this compatibility under the action of the group, which allows you sort of to change, if you think about the way the group acts both on the modular symbols and on the edges. So the integral of the modular form on an edge between R and S can be changed into the integral on the modular form on the standard edge between different R and S by using the group action. But for fixed modular form and any R and S, we already knew this was a bounded function. So therefore, this harmonic function that you get for particular R and S is bounded. Okay, so this is a consequence of the fact that the modular symbols for a given modular form are bounded. And that, in turn, if you like, is a consequence of the fact that the group gamma naught of NP is of finite index in the group gamma naught in the group SL2Z or something like that. So this is a question of checking on the definitions. So just to remind you, what we've done now is we have taken a p-new modular form and extracted from it a harmonic function on the tree, and, well, not quite. I mean, you have to also pick the modular symbol. You have to pick R and S. But for each choice of a path in the upper half plane, we now have a harmonic function on the p-adic upper, I mean, a rigid function on the p-adic upper half plane, which is kind of a strange combination of objects to have. But what it's going to let us do is to interpret p-adic. I mean, we can, the game in a certain sense is to play off the modular symbols with the edges of the tree. And because of the equivariance of the group action, we can kind of trade the group back and forth. So summing over a bunch of edges, this is just a little orientation here, but you can think about it for a moment. Summing these integral from R to S of F over a bunch of edges is the same as instead using the same F, but summing over it for a bunch of transformed R and S's by pulling all of the things back to the standard edge. Okay? So summing over a bunch of edges is like a p-adic integral, and summing a bunch of modular symbols is what goes into the construction of the p-adic L function. Okay, so now I'm going to talk about this work of Darmon and Orton. Orton's paper is in the Pacific Journal of Mathematics, I don't know, relatively recently, isn't it? Canadian Journal of Mathematics, not, sorry, excuse me. Canadian Journal of Mathematics. Okay, so the idea behind this construction is similar to what we did with the LT invariant. Namely, we're going to make two maps between cohomology groups, one of which is going to be non-zero, and we're going to compare them. And they're formally kind of similar. So to simplify the notation, I'm going to let M be this group, the Hom D0 into the linear forms on the space of polynomials. So just to remind you, the modular symbols took three variables. They took a D0 variable, and a P variable, and an edge variable. So I've pushed two of those variables into this M, and all that's left is the edges. So a modular symbol is a function on the edges, but it takes values in M. Okay? And I'm going to define now two cocycles. If I start with a cusp form of level NP, which is new at P, there are going to be 1 cocycles for this group gamma naught P of n with values in this space M. And they look very similar to what we did with the LT invariant. So we take phi f. This is the fancy modular symbol on the tree that we got by taking f, converting it into a function on the whole tree, and then when we integrate from R to S, we get a harmonic function on the tree, and we take that harmonic function on the tree and we integrate it against this function, which, as I mentioned last time, is locally analytic. I mean, because of the fact, we had to pick, I guess I should have said here, A is just some random point in the p-adic upper half plane. So this integral makes sense. It gives you a p-adic number for all this data. And if you work through all the group actions, this turns out to be a 1 cocycle. I mean, what you do is you have to put in sort of gamma 1, gamma 2 here, and then you have to write this as x minus gamma 1, gamma 2 over x minus gamma 1 times x minus gamma 1 over x minus a, and then split apart the logarithm, and then you pull out the gamma into the r minus s's, and anyway, it's a 1 cocycle. And we're going to do the same thing that we did here, but instead of using the p-adic logarithm, we use the p-adic ord. Okay? So it's very similar to what we did in the earlier case, except we have this extra variable floating around, coming from the modular symbols. And we have a much bigger cohomology group, at least apparently a much bigger cohomology group, because instead of having a 1 cocycle for the quaternion algebra group in just this Hom pk minus this finite dimensional representation space, now we have H1 of this much bigger group with coefficients in this great big module. Okay? So the hope is that we can still do what we did before. Just to emphasize this, I've used the fact that the modular symbol was bounded to allow me to take, all I have is the harmonic function on the tree. To turn that into an integral, let's say this log of x minus gamma a over x minus a, I need to use the fact that that function is continuous, for example, in the weight 2 case, and that I can extend, if I have a bounded harmonic function, I can derive from that a linear functional on continuous function. So there's actually a limiting process implicit in this. The cohomology, I picked this A in the upper half plane, but that's why I should take it in H1, because then it's independent of the choice of that A. I've already done this comparison with the construction of LT, namely you got 2 cocycles and you compare them. And if you do this with k equals 2, I'll just point this out here. You see, this is some kind of complicated sum of the log of this thing. In k equals 2, because of the fact the modular symbol is honest integer valued, you could, instead of taking a sum of this logarithm of things multiplied by the values of the modular symbol, you could take the product, there's no p of x then, you could take the product of these rational functions raised to the power the values of the modular symbols. And that's called a multiplicative integral. And then it would have the property that its logarithm would be this, and its p-adic valuation would be that. So that's what Darmon actually does. You can get in the terms of the L invariant, which is log of q over ord of q, you can get q, okay? And then by taking this multiplicative integral. But in higher weight, you can't do that. Now, the strategy to construct the Orton invariant is very similar to what we did before. You still have a Hecke action on this space. It acts on the D0 in M, and it acts in the usual way when you have functions on this group. And the thing you need to show is that if you look in this group for the subspace cut out by the Hecke algebra, where in the same way as it acts on F, and you impose this sign condition, basically you take the odd or the even modular symbols, you need to check that both of these classes now belong to this space, which turns out to be one-dimensional, and this number here is not 0 in that one-dimensional space. And if that happens, you can define an L invariant to be the ratio, basically the number you have to multiply this guy by to get this guy inside this one-dimensional space. And that's called the Orton, or the Darmon-Orton L invariant. Okay? So the form of the definition is very similar to the LT, but the thing itself is quite different. These are in much bigger groups. Now, what is this group? Why is it only one-dimensional? That's has nothing to do with p-adic analysis. I mean, that somehow is a question about modular symbols in general. So let's take a look at that, at this group, and just see how, even though it looks like it's quite a bit bigger than what you would normally expect to see. I mean, if we were in the weight 2 case, you'd really just expect to see H1 gamma naught of NP with constant coefficients, for example. That would be more or less the homology of the modular curve. I mean, ignoring questions about cusps and so forth. But here we have this big module M. So we can make a few remarks about this space. First of all, remember what M is. It's Hom, it's way back here, but it's Hom D0. So these are the weight K, it's the space in which the weight K modular symbols for F live. And the modular symbols for F are what, if you take the gamma naught of M invariants in M, so you take the gamma naught of M invariant maps from D0 into this space, last time in the last lecture I pointed out, that is the space of modular symbols for F. It's a version of the H1 of the modular curve, possibly with some relative information coming from the cusps. But morally speaking, it's the H1 of the modular curve. So if you take gamma naught of N invariants in there, what you're computing somehow is the cohomology or the homology of X naught of N, maybe with some cuspidal stuff. But remember, F is P nu. And so it's not doesn't occur in X naught of N. Okay, that was the whole point. So if we then look for the part of this thing in which the Hecke action agrees with F, it's not there. Okay? So that has to be 0, because this space would basically compute the modular forms of level N. I mean, if we're in the weight 2 case, it would compute essentially the cohomology of X naught of N, and F is not in there. On the other hand, if you do include the P, then this is the two-dimensional space that's in the cohomology of the modular curve that's cut out by F. Two-dimensional, it has a plus part and a minus part. So, so this, we do get something. We get this two-dimensional space. In fact, in a certain sense, I mean, what is this? This is essentially H1. It's the thing I mentioned before. H1 of gamma naught of NP with constant coefficients, the part where the Hecke action is F. It's not quite true because you're doing things relative to the cusps here, but that's close enough. Now, we're in the following situation. We have this tree X, and we have this big group which acts on it. And if you look at the quotient by that action, you get a single edge. But, I mean, you still have a big subgroup of the group acting on that single edge. Basically, you have gamma naught of NP acting still on that edge. And if you think about what the stabilizer of one of the vertices is, well, if you remember from the first lecture, the stabilizer of a vertex is a group like GL2 of ZP. And if you intersect this gamma naught twiddle Pn with GL2 of ZP, then what you're doing is you're imposing the conditions that the A, B, C, and D, which you previously allowed to have p's in the denominator, now they're not allowed to have p's in the denominator anymore. They have to be p-adic integers. So the stabilizers of the vertex look like gamma naught of N. Okay, so you have two, I probably should have drawn this on a picture, but you have an edge, which is stabilized by gamma naught of Pn, and you have two vertices, one of which is stabilized by gamma naught of N, and one of which is stabilized by a conjugate of gamma naught of N, but it's a group which is still isomorphic to gamma naught of N. And you have some stuff on this tree. You want to, now, whenever you're in this situation, you can use the theory of graphs of groups, I think it's called, which is talked about in Sayre's book on trees, to compute cohomology. And, or I guess in fancy terminology, there's some kind of spectral sequence that you get from this, and this would be the sequence of terms of low degree. And what you get out of that theory is the following. You get an exact sequence where you have the gamma naught Pn invariance in M. And then you have the two copies. This corresponds to the edge. So these are sort of the global invariants. Okay? These are the invariants by the vertex stabilizers. This is the invariance by the edge stabilizers. And then you have an H1, sort of a global H1 term is what happens. So these guys we already decided were 0, right? Because F is p nu. And this thing down here, you will have to unwrap a bit, but it turns out also to be 0. I mean, it's still somehow at level n. So the upshot of that is this guy here has to be 0. There are no global invariants, at least of type where the Hecke algebra acts by F. And this group here, which we were the one that we're really interested in, this H1 of this big group with coefficients in this module M, but the part where the Hecke algebra acts through F, is just isomorphic to this two-dimensional modular symbol space. So this is a big reduction of this cohomology group all the way back down to a two-dimensional space of modular symbols associated to F. And remember, it's two-dimensional, but it has this sign operation. I mean, it has a plus part and a minus part. So if I had added the signs here, the plus and minus parts of this are each one-dimensional. So the part we care about in this big group really is one-dimensional, and so this definition of the L invariant that I wanted to give, that was the ratio of the ord and the log, makes sense. Okay? So now you've defined it, but the great thing about this is you can actually prove something instead of just define it. And so the strategy, I mean, I guess the strategy to prove this is you calculate and you do these p-adic integrals. And this proof is in the notes, and you can read about it in Orton's paper. I'm not going to attempt to go through the calculation here. It takes advantage of a lot of clever tricks, of which the principal ones are the geometric series and the telescoping sum. Okay? I think those are the two tricks, and also the fact that you know, things about sums over characters. Would you say that was fair? Yeah. So if you can do the geometric series and the telescoping sum, and you know about the sum over characters, and you can keep your head about you, then you can do this integral. But the idea, I mean, the problem that we have now is you have to compare two cocycles, and that's kind of inconvenient because what you really like to do is compare two numbers. So you can reduce the question to two numbers. This is the general ingredients here. Our form has this p Fourier coefficient, and we choose plus or minus to give us the sign of the character that we're, I think I have two, I mean, there's a Dirichlet character floating around here, and I need to make sure, this statement here says that I'm choosing a Dirichlet character such that chi of p is the sign which appears in the AP of the form F. That's necessary to put you into the condition where there is supposed to be a conjecture at all. Then the plus or minus is the character of -1. And you have some numbers here. The order, C is the conductor of the character chi, and you need to know the order of p squared modulo C. And then you can make this element in the group G, which is a translation in the tree along a line from the point minus nu over C to infinity. And you also take a particular polynomial if you're doing the higher weight case, namely this one. This is all really part of a trick. And the trick is, instead of trying to compute the cocycles, you evaluate them at this data. Namely, you plug in this gamma that I just gave you, and you evaluate it on this polynomial that I just gave you, and you integrate along this particular modular symbol that I just gave you. So these are particular values of those two cocycles. And the great thing is that if you had changed either LC or OC by a coboundary, coboundaries vanish on this data. Okay, that's an exercise, basically because the polynomial that you chose is fixed. But I mean, this is sort of takes advantage of the fact that various groups fix various things in this diagram. So now these things, these numbers here, they are they're actual numbers extracted from the cocycles that only depend on the cohomology class of the cocycles. So if we can show that this is a certain number times this, then it must be the case that this is that number times that. Of course, they could be 0 or something, but that actually doesn't happen. because the first calculation that you do, if you're determined to carry this out, is you compute the one with ORD. So I had defined the one with ORD as you integrate the ORD of x minus gamma a over x minus a against this modular symbol valued measure. But as I pointed out earlier, when you integrate x minus gamma a over x minus a, take the ORD of that, and you integrate that over the boundary, it turns out to just be a sum of values along the tree. This locally constant function that you're integrating, when you sort of sort through what's going on, you can reinterpret that as a sum along the tree. So this first integral, which I'll flip back to, although I may regret that, this lower one here, which has ORD in it, think about weight 2, so forget the polynomial. You're integrating this ORD thing, turns out to be a sum of the values of the modular symbol between the vertex where a goes and the vertex where gamma a goes. So it's a finite sum. And if you think about that hideous thing that I put up earlier, which expressed the algebraic part of the special value of the L function in terms of modular symbols, if you sort through what that thing is, this thing here, which is one of these integrals, for if it's a particular value, one of the integrals, it's a certain sum involving modular symbols, which, when summed against this character, actually turns out to be that thing that I described earlier. So in other words, the algebraic part of the special value is very closely related to that OC, the ORD cocycle. So that's good, right? Because we're trying to, I mean, the thing that defines the LO is supposed to be the derivative of the p-adic L function divided by the algebraic value, and so then we're sort of halfway there. The other part of the calculation, this maybe won't shock you, is that if you do the one that involves the logarithm, and you take this sum, you actually get the special value of the derivative of the p-adic L function. Now, this may really sound surprising, but if you think back long ago to the earlier slide that I'm sure nobody can remember, I don't know if it's worth flipping all the way back to it. Let's see if we can find it. I think it's here somewhere. Yeah, this thing. This is the weight 2 case. This is what the integral which defines the p-adic, the derivative of the p-adic L function looks like. It's an integral of the log of something against a limiting of a sum of the logarithm of something times values of modular symbols. Well, at least in some very vague sense, that's what the LC thing is also. It's an integral of the logarithm of something times this measure on the tree, which is, remember, as I said, even though that integral looks like you're passing to farther and farther and farther out on the tree and holding the r minus s constant, you can reinterpret that as pulling everything back to the basic edge and summing a complicated function against values of the modular symbols where the r and s change. And that somehow is what you do. You work this out in the calculation. And if we flip back, it turns out that that actually this thing is the algebraic part of the special value. So in particular, think about what Orton and Darmon have proved here. They've proved that there is a number such that this relation holds. And the number doesn't depend on this character psi, because the number is a relation here between the Li and the OCI, which existed before you summed over the character values, okay? So they're like, maybe you could sort of in some way think of them as the partial L functions or something. You have a relation there. So whichever psi you pick, you still have this same number appearing. And the original exceptional zero conjecture was phrased in that way. It said that there was some number such that these two things were related in this way, and the number kind of only was independent of any twists that went into it. Now, it's actually much stronger than that. I mean, because some of those other L invariants are actually, I mean, which are all equal to one another, because from their construction are actual invariants, let's say, of the local Galois representation associated to F, so that there is an actual interpretation of those numbers. But even though historically this one was done last, it's elementary, and right, there's no, it doesn't use any information that wasn't known back at the time that the original conjecture was made. It just uses modular symbols and integration on the p-adic upper half plane, and it gets the conjecture. So I think it's a really very nice result. Now, I should say, Darmon did this in weight 2. And in that case, you get even more, namely, you actually get, isn't this right? Do you get that this is log q over org q? No, you don't. You still need to know that from Greenberg and Stevens, yeah. So you still, for weight 2, you find this number, but you still need to rely on Greenberg and Stevens to know that it is log q over org q. So I just want to emphasize this, especially for the people working on the project. You know, it's easy, it's tempting to think, and I've made this mistake now, it's hard for me to get this straight in my head. There's this LT thing, right, which is defined by these integrals on the p-adic upper half plane. And there's this LO thing, which is defined by integrals of a similar sort. They have nothing to do with one another. I mean, except long after the fact, when they turn out to be equal. But in terms of how they're computed, there's no relationship that you can see between what's going on. So for example, the numbers which are going into this calculation are periods on the complex upper half plane. Okay? They have nothing somehow to do with Shimura curves or anything else. Okay, so I think this is a good place to stop. I'll pick up on whatever day, Wednesday, right? I'll pick up on Wednesday with revisiting these topics from Broy's point of view. I mean, I said that the Broy has his own construction of the L invariant. In a certain sense, that's not fair. What Broy has is another construction of this L invariant, but in a context which sort of shows you the significance of this LO for what's called the p-adic Langlands correspondence, or the hoped for p-adic Langlands correspondence. So that's what I'll outline in the last talk. Thanks.